Hello and welcome to a new session of Physics by Cloud Tutors powered by Connecting the Dots. Today's topic is magnetic effect of electric current. But of course, we will be continuing from our previous session on this same topic. So before we get into today's actual session, let's look at a few important points for this chapter when it comes to examination point of view. Alright, this program is conducted to help grade 10 students to prepare for their board examinations. So we will look at these important points from the examination point of view when it comes to this chapter. Alright, so a few things that we can remember while preparing for this chapter is that it holds an importance or a weightage of 4 to 7 marks. 1 or 2 marker questions can be based on your definitions from the chapter, or very simple circuit diagrams, or very simple magnetic field line patterns that we have looked at in previous sessions. That could also be a 1 marker question where you will be asked to draw the magnetic field lines pattern, from what direction to what direction do they go, and few things like that. While long answer questions are majorly from your electric motor part or electric generator part, which we will be looking at today's session and in the next session as well. Alright, so to begin with, we will definitely look at a sample mind map wherein we have made this list of points or list of topics which need to be covered under this chapter, and today we will be looking at these two highlighted topics. Alright, so without further ado, let's get started with today's session. Let's do a quick recap of what we have learned so far. We have learned what is magnetic field, how are these magnetic field lines going from what pole to what pole. We have understood that a given magnet will have 2 poles, one is a north pole and another is a south pole. We have understood the properties of these poles. Like poles repel each other, unlike poles attract each other. Magnetic force which is exerted by a magnet on another magnetic substance or another magnet is basically a non-contact force, right? We don't have to bring 2 magnets or 1 magnet and another magnetic substance with with contact with each other. Even without the contact with each of these substances, what happens, you see that you feel that there is a attractive or a repulsive force existing between them, right? This is magnetic force of attraction or repulsion depending upon what poles are close by. If it's north and north pole or like poles, they will repel. If it's unlike poles, they will attract each other. Now that we have understood what and how a magnet works and what is magnetic field, properties of magnetic field lines, we also looked at the magnetic effect of electric current. So as we have looked at the experiment videos, and we also did one of the experiments, simple experiments, where we saw that the magnetic needle actually deviated, right? So why did that happen? Because when we start passing the electric current through a conductor, what happens is that there is a magnetic field induced due to change in electric field, due to moving charges inside the conductor. There is a magnetic field induced around the copper wire, which we have seen in our previous session as well. So what is the direction of the magnetic field? What is the pattern of the magnetic field lines in such induced cases is given by Maxwell's right hand thumb rule. So Maxwell's right hand thumb rule, as you can see it on the screen, and we also discussed in detail in our last session, that when we hold a conductor using our right hand and stretch out our thumb in the direction of the current, my curling fingers basically gives us the direction of the induced magnetic field lines, right? If I hold the conductor in this manner and I reverse the direction of the current, again my outstretched thumb of my right hand shows the direction of the current. But what you notice here is that the direction of the magnetic field lines also have been reversed, right? So this is magnetic effect of current, and the direction of the magnetic field induced around a current carrying conductor a straight current carrying conductor is given by Maxwell's right hand thumb rule. So with this, we also saw what happens if we wind the same conductor, same copper wire into a coil. Even then, as you can see it on the screen, as and when we pass the electric current, what happens is that there is a magnetic field that is induced around this coil. Again, the same same rule, that is Maxwell's right hand thumb rule, is applied in order to determine the direction and the pattern of magnetic field induced around this copper coil. Alright, as you can see it on the screen, as and when we pass the electric current, there is magnetic field lines pattern that are formed by the iron filings which are randomly spread across around this electric coil, right, a copper coil. So here it becomes an electromagnet, right? So what is an electromagnet? Electromagnet is a temporary magnet which is basically a copper wire or any kind of conductor wherein we pass the electric current and there will be a magnetic field which is induced around this current carrying conductor, and this can be used as an electromagnet. Alright. Now, if it is a coil, there can be, and you have already seen it in the video also, we conducted an experiment using a copper coil and a permanent magnet. You saw that there was a force of attraction and force of repulsion in the same coil when we held it differently, as in when we reverse the direction of the electric current passing through the coil. So why does that happen? Because the two magnets, basically the copper coil, once we start passing the electric current, becomes an electromagnet and starts acting as a magnet itself, wherein it will have a north pole and it will have a south pole. So how do we know on what phase of the coil will have north pole and what phase of the coil will have south pole? For that, we can make use of something called as clock phase rule. So what does this clock phase rule state? If at all we pass the electric current in the clockwise direction, on that phase, the coil which is facing us, the face of the coil which is towards us, will have south pole of the magnetic field induced, and if the current is passed in the anti-clockwise direction, then the same phase will have north pole of the magnetic field, north pole of the induced magnetic field facing us, right? So what is happening here? When we reverse the direction of the electric current, the magnetic field induced has also reversed its direction, and hence we can actually reverse the poles of this electromagnet, which we cannot do in our permanent magnets. Which brings us to another kind of electromagnet that is used very commonly, that is a solenoid. What is a solenoid? A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called as a solenoid. Since solenoid is in the shape of a cylinder and it exactly acts as a bar magnet. Why? Because the kind of magnetic field induced around this coil or this kind of arrangement acts exactly as a magnetic field which is around a bar magnet. Hence, a bar magnet, wherever we use bar magnets which is not very strong as it is, we can definitely make use of a solenoid, wherein we have advantages like we can actually vary the amount of strength of the magnetic field by varying the amount of current passing through the coil, and also we can reverse the poles of the magnetic field induced around the solenoid by reversing the direction of the current. Right? So these are few advantages and also few comparisons that we discussed between a permanent magnet and an electromagnet, right? We know that an electromagnet is temporary magnet, whereas a permanent magnet always has its magnetic field. So storage also becomes slightly challenging if it's a very huge and strong magnet, right? Wherein if we have to store an electromagnet, it is just a copper wire, insulated copper wire wound into a huge coil, and we just have to find a voltage source to pass the electric current through it, and hence we can basically make an electromagnet very easily. right? And also it produces a temporary magnetic field, whereas the permanent magnet always has a magnetic field around it, and strength of the magnetic field can be varied in this case. What case? That is the electromagnetic case. But in the case of permanent magnet, we cannot do that. Whatever the nature and whatever the strength of the magnetic field provided by a given permanent magnet is, that can never be varied as such, whereas we have that facility or that liberty using an electromagnet. All right. Now, with this, let's just try and answer one or two practice questions based on these topics that we have done in our previous session and also discussed in this session. So state the rule used to determine the direction of magnetic field produced around a straight conductor carrying current. This was asked quite frequently, as you can see on the screen, and it could be asked as a 1-marker question or a 2-marker question as well. All right, the answer would be, it is Maxwell's right hand thumb rule. All right, and it states that if the current carrying conductor is imagined to be held in the right hand such that the thumb points in the direction of the current, then the curled fingers. So as we have discussed in the previous session, if you imagine this to be the a copper wire which is straight, current carrying conductor, if I hold it in my right hand like this and outstretch my thumb in this fashion, my outstretched thumb shows you the direction of the electric current, and my curling fingers basically tell you the direction of the magnetic field induced around this straight current carrying conductor. And this is Maxwell's right hand thumb rule. All right. Now, next one. So here is a question which is not definition based, or which is not you don't have to write anything but you need to remember the kind of pattern of the magnetic field, that is induced magnetic field, and the magnetic field lines that are there around the current carrying conductor when we pass the current through it. So what is the question? Draw the pattern of the field lines of magnetic field through and around a current carrying solenoid. So as you can see it here, a solenoid, what is a solenoid? A solenoid is a very closely wound insulated copper wire in the form of a cylinder, or we call this as a helical shape. Okay, and when we connect the two ends of this insulated copper wire to a battery or a voltage source and the current starts flowing through this, it basically acts as a bar magnet. So as you can see here, whatever the kind of field lines that we are showing, it is exactly the same as a bar magnet's magnetic field lines, correct? Yes, so you see that the direction of the magnetic field line is going from north pole to south pole. That is also an important point to remember while you're drawing the pattern of the magnetic field lines around a given magnet or an electromagnet. So the lines have to show that, or the arrow marks have to point from north to south pole of the given electromagnet or a bar magnet. If you are ever asked to draw the magnetic field lines pattern for a given electromagnet, please remember that the direction of these lines have to go from north pole of the magnet to the south pole of the magnet. All right. Now, state the factors affecting the strength of the magnetic field in a solenoid. Basically, it's an electromagnet, we know that. So what are they asking you? They are asking you, what are the factors that actually determine the kind of magnetic field that is induced around a solenoid? Is it current? Is it the kind of wire that we use? What is it? And also state the rule which gives the direction of the magnetic field. So for that, here is your answer. The strength of the magnetic field at a point due to a current carrying conductor depends on. So since it's a 2-marker question, you need to structure your answer properly. Write it point wise always. It always helps the evaluator to differentiate between your beginning of the answer, and also it creates a very clear picture without any confusion. Alright, so you can always remember, and I think you should always remember, that science answers have to be to the point, and also write it bullet point wise. Do not form a paragraph and make the evaluator read everything. Alright. Now, what is the first point? First factor that that basically determines the strength of the magnetic field induced around the solenoid is strength of the electric current flowing through the conductor. Higher the amount of electric current flowing through a conductor, larger is the amount of, or stronger is the kind of magnetic field that is induced in the coil. I'm sorry, not in the coil, around the coil. Next, number of turns in the solenoid. Why is this important? Because when we increase the number of turns, we are basically increasing the length of the wire, right? So when we increase the length of the wire, we are passing the electric current for a longer time and through a longer distance. Hence, there is for a longer amount of time, the electric field keeps on changing, or the charges keep on moving. Hence, the induction of the magnetic field also sustains. Correct? So, number of turns in a coil can be increased or decreased depending upon the kind of magnetic field that we need. Higher the number of turns in the coil, stronger is the kind of magnetic field that is induced around the solenoid. Now, what is the rule that basically determines the direction of the magnetic field? It is again Maxwell's right hand thumb rule. Alright, so with this, let's look at a small video wherein we can actually see the difference when we increase or decrease the these two factors, or when we vary the these two factors, and you can actually see the kind of variation that occurs in the magnetic field. All right, so here is there is a cell here that acts as the voltage source, and there is a coil that is connected to this cell. So you see that there is basically it is at 0 volt now, so there is no electric current flowing through it. So when I increase the voltage, you see that there is a magnetic field that is induced around this coil. So as in when I decrease the voltage, what happens? The amount of electric current flowing through the coil decreases, and hence the strength of the magnetic field also decreases. So you see, when I increase it to 10 volt, the amount of current flowing through it increased, that is the strength of the current flowing through the coil also increased, and hence the strength of the magnetic field which is induced around this coil also increased, right? So this is how these two factors basically determine the kind of magnetic field which is induced around the solenoid. So with this, we come to our next topic, that is the force experienced by a current carrying conductor when it is kept in magnetic field of another magnet. Now, what is this and how is this possible? So you can imagine, now that we know what is magnetic effect of electric current, we have discussed it n number of times already, but let me repeat it. Whenever there is a flow of charges or moving charges, basically create a changing electric field or varying electric field through a given conductor. Because of the continuous variation of this electric field around the moving charges, there is a magnetic field that is induced around the current carrying conductor. Now, this current carrying conductor can also act as a magnet, which is called as the electromagnet. Now, when we keep this electromagnet in the vicinity or in the surrounding of another magnet, what happens? So because there are two magnetic fields now, please remember that, because there is an electromagnet which has its own magnetic field, which is an induced field, and when we keep it in the vicinity, or when we keep this closer to another magnet which has its own magnetic field, there is this interaction of the magnetic fields due to the permanent magnet and due to the induced magnetic field as well. Because of this interaction, the current carrying conductor, as you can see it on the screen here, this experiences a pull or a push. That is, this basically experiences a force due to the interaction of the magnetic fields of these two magnets. What are the two magnets? One is the current carrying conductor itself, which acts as an electromagnet, and another is the permanent magnet, which we have kept closer to this entire setup. To understand it and to look at it more closely, to understand it better, let's watch this video. So as you can see it on the screen, what this person has done is set up the same kind of experiment that was shown in the previous screen. As you can see here, this basically is a huge magnet. You see there is a huge horseshoe shaped permanent magnet around which he has set up this simple circuit. Here is the battery, as you can see it on the, here is a battery, and through which is used as a voltage source, and here he has still not made the connections with the battery, and he is just trying to explain what is the setup. So here there is a wire which is going through this particular path, and it is actually connected to a copper rod. Again, copper rod is another conductor through which the current actually flows. So what he is trying to show us here is according to whatever we discussed, the force experienced by a current carrying conductor when it is kept in the vicinity of another magnet, it basically experiences a pull or a push due to the interaction of two magnetic fields. Which are the two magnetic fields? One is the magnetic field due to the permanent magnet, and another is the induced magnetic field due to the current carrying conductor, around the current carrying conductor, right? So now when I play this video, you see that this wire, he's making the connection here, right? So this copper rod basically will be pulled or pushed in depending upon the direction of the current. We will discuss more on the direction of the current, but let's just watch this video for now. All right, so as he makes the connection here, you see that the copper rod is pushed out or pulled in. So you saw that the copper rod is pulled in, correct? Now let's see what happens when he reverses the direction of electric current passing through the same setup. You saw that the copper rod is pushed out now, correct? Right? So why does this happen? With this, we see that there is clearly some kind of pull or a push that is acting on the copper wire when we keep this entire setup, that is a current carrying conductor, which is the copper rod or a wire, in the vicinity of another strong magnetic field. Because there is an interaction of two magnetic fields, that is, one is the induced magnetic field around the copper rod and another is the magnetic field due to the permanent magnet itself, there is a force experienced by this copper rod. It basically gets attracted or repelled depending upon what kind of pole has the induced field that is acting around the conductor. If we reverse the direction of the current, basically you saw that the direction of the pull or the direction of the force basically changed, correct? Now this direction of the pull or push is given by another rule called as Fleming's left hand rule. As you can see it on the screen, what does Fleming's left hand rule state? Fleming's left hand rule basically asks, first is that stretch your middle finger, forefinger and the thumb of your left hand in this fashion so that they are all mutually perpendicular. Alright, so my forefinger, my middle finger and my thumb are all at 90 degrees to each other. So in this case, what happens? How do I actually tell the direction? So here in the previous setup that you saw, we know the direction of the electric current. From what end to what end are we actually sending the electric current? And we also know the direction of the induced magnetic field using Maxwell's thumb rule, correct? So we know these two. Only unknown thing that we saw over there was the pull or the push that basically acts on the copper rod, that is the current carrying conductor. It experiences a force due to the interaction of the two magnetic fields, because there are two magnets present over there. One is the electromagnet and another is the permanent magnet. So direction of this force experienced by the conductor kept in the magnetic field of another magnet is given by my thumb here. Alright, so as you can see it here on the picture, the direction of the force is given by the thumb. The direction of the magnetic field and the direction of the current is basically known to us, correct? So if I stretch, or if anyone we can stretch our left hand such that our forefinger, middle finger and the thumb are in right angles to each other or mutually perpendicular, while the forefinger shows us the direction of the induced magnetic field, middle finger tells us the direction of the current, and finally the thumb shows us the direction of the force experienced by the current carrying conductor when we keep this current carrying conductor in the vicinity of another magnet or in another magnetic field. Alright, where is this force produced from? It is just because of the interaction of the two magnetic fields. One is due to the electromagnet and another is the another permanent magnet, or it could be another electromagnet also. So when we keep two magnets in interaction with each other, or when we keep two magnets close by to each other, there is definitely two magnetic fields which are interacting, correct? So what happens if I keep two bar magnets closer to each other? According to what poles are they are closer to on one of these magnets? If they have like poles facing the other magnet, they repel. If there are unlike poles, they'll be attracting. So some kind of magnetic force is experienced by these two, right? So similarly, when there is a current carrying conductor which acts as an electromagnet is kept in another magnetic field, the current carrying conductor itself experiences a mechanical force due to the interaction of these two magnetic fields, and the direction of this mechanical force experienced by the current carrying conductor is given by Fleming's left hand rule. Again, let me repeat the rule. When you stretch your left hand forefinger, middle finger and the thumb mutually perpendicular to each other, the current is shown, or the current direction is shown by the middle finger, while the forefinger shows you the direction of the magnetic field induced around it, and finally the thumb shows you the direction of the mechanical force experienced by the current carrying conductor. Alright, now with this, let's answer this very simple one marker question. What is it? A wire AB carrying a current placed in the magnetic field. Find the direction of the force on the wire. So you see that here is a current carrying conductor, that is AB is a current carrying conductor. So when I apply Maxwell's thumb rule, what will be the direction of the magnetic field? You see these red arrows. Basically, these arrows are showing the direction of the magnetic field due to the permanent magnets kept around it. But what will be the direction of the magnetic field around the current carrying conductor? It will be shown by the curling fingers, correct? Right? Now that I know the direction of the current here, I can use Fleming's right hand rule and also tell the direction of the mechanical force experienced by this straight current carrying conductor. So let's look at it. So what is the finger that actually shows you the direction of the current according to Fleming's left hand rule? It is our middle finger. So if I keep it like this, this should be the current direction, this should be the direction of the magnetic field, and outstretched thumb, which is towards me. Correct? So when I keep it on the screen like this, if you draw the same diagram and keep your left hand in this fashion, you see that this outstretched thumb is towards yourself. So that will be the direction of the mechanical force experienced by the current carrying conductor when it is kept in the vicinity of another permanent magnet. Alright? Now, since we know that there is a mechanical force that is experienced by a current carrying conductor, can we put this to use? Can we harness this mechanical force? Basically, what is happening here is some form of energy is getting converted into some other form of energy. Can we harness this and make use of this particular phenomena in any place in our daily lives? Most definitely yes, and that is where an electric motor comes into picture. An electric motor is such a useful device, and we use it in our daily lives even though we do not know or we are not aware that we are using an electric motor, and which works on the principle of magnetic effect of electric current, and also a force is experienced by a conductor when kept in the vicinity of another magnet. Both the combination principle basically is the working principle of an electric motor. So let's take a look at it. So what is an electric motor? Electric motor is a simple device which basically converts electrical energy into mechanical energy. Why electrical energy? As in when we pass the electric current through a given copper wire, only then there is a magnetic field that is induced. Only when we keep this entire setup in the vicinity of another magnet, or when we keep the entire setup in another magnetic field, there is an interaction, and hence the copper wire, the conductor itself, basically experiences a mechanical force. Correct? So electrical energy is basically getting converted into mechanical form of energy. Hence, how do we define electric motor? Electric motor is the device which converts electrical energy into mechanical energy. Alright, we'll come back to this setup, but let's look at one or two methods. How can we build a very simple electric motor? Alright. So a simple electric motor can be built using a copper wire. Only three things. Of course, if you can find these three things at home, I'm sure two of them can actually be found at home, and all you need is another magnet, right? You need two magnets and one current carrying conductor. So you need a cell which acts as the voltage source, and you need a copper wire which is the conductor, and you need a magnet which has to have an interacting field, right? Because you create an electromagnet, and you need to have another permanent magnet wherein you create the interaction between these two magnetic fields so that you see the mechanical force in effect, right? So here is an example. So all you can see here is this particular one is a huge magnet on top of which we have kept one simple Duracell, right? This cell is kept on top of it, and the copper wire is wound in such a fashion that it is in contact with the cell. Hence, the current starts flowing through the copper wire. But as you can see here, the copper wire is rotating, correct? In the previous video, you saw that the copper rod was just pulled or pushed. There was a force of attraction or force of repulsion. But how is this rotating? And why is this happening? Now, so in general sense, a force can be a pull or a push. Correct? We have already studied this in your 9th standard, and you know enough about force, I'm sure. So any force, basically, if applied on an object, if I apply force in this direction, it will be pushed in the same direction as that of the force. If I apply more force on the opposite direction, it will be pushed in the same direction as that of F dash. Correct? Two forces acting here. If at all both the forces are balanced, what happens to the object? The object does not move. We have learned this in your 9th standard when we studied balanced and unbalanced force. I'm sure you all of you can recall. Correct. Now, what I do is, let's erase this and let's keep the object alone. Okay. So what I do is, I fix this object at the center. Fixing an object or fixing any of the body at one point is called as pivoting. Okay. So I fix this particular object. This is a pen, right? You can see that it has a horizontal structure and it is slim in nature, and if I hold it like this and fix it, and if I apply force here, I'm pushing it, correct? So if I apply force, because it is fixed at one point, what happens? It cannot actually move forward or backward, right? There will be no translational movement, translational motion. Translational motion is nothing but motion in a straight line or rectilinear motion, correct? So whenever an object experiences a force, it basically moves forward or backward. That happens only when the object is not fixed at one of its ends or at some point in its body. When I fix the object at some point in its body, say for example at the center here, when I give a push, I am applying a normal horizontal force, ordinary horizontal force. But what is happening? You see that the pen is actually turning, correct? So what happens when I apply an ordinary horizontal force on an object which is fixed or pivoted at one point is that it creates a turning effect. It is called as the moment of force, correct? So this is what happens in an example when you take the example of door. What is a door? Let me try and draw it. I'm sorry for my poor drawing skills, but let me try and depict a door as well as possible. Okay, so as you can see here, let me draw it properly so that you can see it properly. So let's say this is a door, and you know that there are door hinges. It is fixed at one point. One side of the door is actually fixed, correct? And there is a knob here, correct? Or a handle, door handle. So what do you essentially do when you have to open or close the door? You pull it to open the door, you push it to close the door, right? Here, notice that you are applying ordinary horizontal force each time if you have to open or close the door. But what does the door do? The door actually does not move forward or backward in this direction. It does not perform a motion in a straight line. It basically turns, closes and opens like this, correct? Why? Because it is fixed at this point or fixed at one end. So the ordinary pull or a push basically creates a turning effect on the door, and this turning effect is called as moment of force. Now, what happens here? Why am I explaining all of this when it comes to a motor or an electromagnet or interacting magnetic fields? Because I need you to understand why is there a rotation produced in this particular coil that you see on the screen when we keep to one electromagnet and another magnet in each other's vicinity. So we understood that there is a force acting on a conductor which is kept in the magnetic field of another magnet, right? So this force basically should push or pull the current carrying conductor, which actually happened when that is what you saw on in that video. But here there is a rotation. Why is that? Because of this turning effect of the force. Because we have fixed the coil at one end, it is actually producing a turning effect in the coil, and this is exactly why it is rotating. Now, one force can actually turn the given object which is pivoted at one point, but to produce rotation we need two equivalent opposite forces so that they are pushed and pulled at the same time. Hence there is a rotation that is produced, as you can see it on the screen. This is what exactly happens in a given electric motor. The coil is basically pushed and pulled at the same time. Ordinary mechanical horizontal force which are opposite but same in magnitude are acting on the coil simultaneously, and hence it is actually rotating. You might have seen in the noticed in one of the any of the parks that are closer to your place, you see that there will be a gate like this, correct? So a person has to, if a person has to go in, this entire gate has to rotate because it is fixed or pivoted at the center. So in order to rotate the gate, one person will go in, another person can come out. So basically there is a push and the pull acting at simultaneously on the object which is pivoted at the center, hence producing a rotation, right? This is exactly what happens in case of electric motor. All right, this is one way of building a simple electric motor. Another one, as you can see here, is much more, a little more sophisticated. It's again the same principle. Here what we have done is we have used the copper wire and have wound it into a coil, and the two ends of the coil is connected to the two ends of the battery here, or the Duracell voltage source here. And as in when we actually pass the electric current, we make the connection, what happens, there is an electric current that is flowing through the coil. It induces a magnetic field, and when we place another magnet, the black thing that you see on the screen is a magnet, and you actually are creating an interactive two magnetic fields, or interaction between two magnetic fields, basically due to which the coil starts rotating. There is a push and a pull, which basically produces a rotation. These are two ordinary forces which are acting simultaneously on the coil and hence produces rotation. All right. So this basic principle of working of an electric motor is the combination of magnetic effect of electric current. Why do we need that, or why do I say that is also a combination? Because once we only pass the electric current and it induces a magnetic field in the coil, only then there is an electromagnet that is formed, correct? If we keep two magnets closer to each other, there is only magnetic force that is acting on each other. There is no current carrying conductor which is pushed over there, right? So hence we need an electromagnet and another permanent magnet in which or around which there is a strong magnetic field which interacts with the induced magnetic field of the electromagnet, and hence this entire setup is created in this fashion. All right, now let's understand the working and construction of an electric motor. As we have already understood the working principle of an electric motor, let's understand slight details of construction of electric motor. So as you can see here, the setup contains a huge permanent magnet, a strong permanent magnet, and there is a copper coil in the form of a rectangle, correct? So this rectangle coil is basically attached to a split ring. So as you can see, there is a gap here, right? It's a split ring, and there is X and Y brushes, conducting brushes, which are necessary for the connection to be made. So this split ring basically acts as a commutator. I will come to it. Why do we need a commutator here? In a while. We have conducting brushes. There is axle around which the coil basically rotates, and these two brushes, that is the X and Y brushes, are connected to the two ends of the battery, and there is a key here. All right, now that we have understood this setup, let me go back to this one. All right, so as you can see here, there is a split ring, as you can see the coil rotating, right? So what is happening here? There is north pole and south pole of the magnet in between which the electromagnet has been placed. So as in when we pass the electric current, this end of the coil, which is, if I can draw it here and show it to you, this end of the coil, let's call this A, B, C, D. So once these conducting brushes make the connection using the split ring, which acts as a commutator. Commutator is basically a key which has 4 keys, using which we can actually reverse the direction of the electric current. I think we have discussed in our electricity chapter also. So what happens here is when we pass the electric current here in this direction, okay, so let's check and apply Fleming's left hand rule for arm AB or for side AB of this rectangular coil. So AB has the direction of the current flowing in this direction, right? So if I apply Fleming's left hand rule, my middle finger has to show the direction of the electric current, and forefinger shows you the direction of the induced magnetic field around the coil or the current carrying conductor, and my stretched thumb, which is in the downward direction, shows you the direction of the force experienced by AB arm of this coil. Hence you see in the picture that the coil, the AB arm or AB side of the coil basically is pushed down, correct? And the opposite side of the coil, that is CD, where the direction of the electric current is in the direction opposite to that of AB, it is basically pushed up. It experiences a mechanical force which is pushing CD side up, and which is pushing another mechanical force which is actually pulling the side AB here, correct? So once it actually, the entire coil actually attains a or comes to a vertical side of it, what happens? It starts rotating and it comes in this pattern. Here there is a split ring which basically cuts down the electric current through the coil, right? So in that case, the coil should stop rotating, but it doesn't. Why? Because the force which is actually pushing and pulling two sides of this coil has already given enough momentum to this rectangular coil to rotate completely or complete one rotation. So what happens? CD comes here and AB goes here, and hence the direction of the electric current flowing through CD side is now in this direction, and hence it again experiences a downward force, and AB, which has a direction of the electric current flowing towards me, which is in opposite direction of the side CD, it experiences a force which is upwards now. This cycle basically continues until and unless we stop the flow of electric current completely. Hence, what happens here is the electrical energy is basically getting converted into mechanical energy, which is started rotating the electrical coil or the copper coil, which is connected in this fashion, and hence this rotational pattern of it, or this mechanical force which is basically pushing and pulling and hence creating a rotation on this coil, can be harnessed in the form of mechanical energy, and hence electric motor has enormous applications. As in when we think about an electric motor where the electric current is or electrical energy is converted into mechanical energy, we can think about n number of household electrical appliances that we use day in and day out. Let's look at these electrical appliances which we use day in and day out in our life. So what are electrical motors used for? One, that is a fan, electric fan. I'm sure all of you use at your home. This is a table fan that is shown in the picture, but there can be ceiling fans. There are many other forms of electrical fans or rotatory objects that we use in our daily lives. Say for example a dishwasher or a washing machine, right? Or a mixer grinder, wherein this particular mechanical energy is harnessed because there is an electric motor which is fit into these devices or these appliances, which converts electrical energy. As in when we pass the current through the electric motor, what happens? It basically starts rotating, right? And hence anything that basically can be worked in the rotatory motion or made use of in this rotatory motion that we are actually looking at in the pictures, right? So a mixer grinder uses an electric motor, a fan uses an electric motor, a washing machine uses an electric motor. The smallest of the among these pictures is a small motor that can be used in an electric brush, right? As you can see here in this picture, there is a rotation that is actually required for an electric brush to start cleaning your teeth. Instead of we mechanically doing it or manually cleaning our teeth, basically if you just run your electric brush through your teeth, it starts rotating and hence it starts cleaning your teeth. So here is also another application of electric motor wherein we convert electrical energy into mechanical form of energy. Alright, these are very few applications that I've shown you, but electric motor is almost there in every appliance that you can think of. They are there in your smartphones. Why do we use an electric motor in our smartphones? Because the electric motor helps or basically does a job of vibration when we keep it on the vibrating mode, right? So many applications of electric motor are found to be in our daily lives, and hence also we understand where are we using this mechanical effect of electric current and the force experienced by an conductor carrying the electric current. These two principles and phenomena which were discovered, one by Hans Richard Oersted, and another which was the direction of the electric current, the direction of the mechanical force experienced by a copper wire or a current carrying conductor was given by Flemings. So these two are extremely important phenomena which was given to us, and the applications are enormous, and I don't think we would be living the same kind of life that we do today without these applications or without electric motors in our lives. Alright, so let's try and answer one or two practice questions. Again, when it comes to long answer questions, as we have discussed in the beginning of this session and the previous session, long answer questions are usually based on the construction and working principle of your electric motor and electric generator also when it comes to this chapter. Okay, so electric generator will be discussed in your next session, but electric motor, as we have discussed today, please understand the working principle and the construction of the electric motor well, and put it into correct words. Write down the points well so that there are no confusions. So they are usually asked in the form of 3 marker or 4 marker with a combination of another 1 or 2 marker to make it a 5 marker totally or a 4 marker totally. Alright. Now let's try and answer this question. State the rule to determine the direction of the force experienced by a current carrying straight conductor placed in a magnetic field which is perpendicular to it. Right? So this is, we know that it is given by Fleming's left hand rule. I would suggest, if it's a 2 marker question, you can write down the statement and draw a representative diagram. So if this is your magnetic field is basically represented as B. This is just like how we represent electric current as I. So magnetic field is a vector quantity, as we have discussed already. It definitely has some magnitude and also direction. Correct? So magnetic field is represented as B, and the direction of the mechanical force experienced by the conductor is upwards, and this should be your current I. Right? So if at all you cannot draw a proper picture as such, if at least you need to show these directions and also point the direction of the force experienced by this current carrying conductor when kept in another magnetic field, and also write the proper rule. So what does it state? The direction of the force on a current carrying conductor is given by Fleming's left hand rule. According to this rule, stretch thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular to each other. If forefinger represents, it should be represents direction of the magnetic field, the middle finger represents the direction of the current, and then the thumb will point in the direction of the motion or the force acting on the conductor. Motion of the conductor is also a right way to put it across, because when the force experienced by the conductor basically pushes it or pulls it, you see that the conductor moves, correct? That also you can write it in this particular format. All right, so with this we come to end of today's session, and let's quickly summarize what are the things that we have learned today. So first thing that we learned today, or a new topic that we started today, was force acting on a given conductor. So what kind of force acts on a given conductor when it is kept in another magnetic field, and why does it happen? Because it happens due to the interaction of the two magnetic fields. One is the magnetic field induced due to the electromagnet that we have kept in the setup, and another is the magnetic field of the given permanent magnet, or it could be another given permanent magnet. It cannot be another electromagnet, right? Another thing important thing that we learned is the application of this particular principle, or the combination of magnetic effect of electric current and the force experienced by the current carrying conductor basically gives us electric motor. We also understood why is there a rotation produced in an electric motor, right? So with this we come to end of today's session. Let's meet up in our next session. Till then, thank you.